Just not here yet.
Pardon me?
Went to Carter, went to Florida.
Yeah, she's not gonna be here.
That's just Carter.
She's at her board.
Yeah, Junior's
Yeah.
not here.
She's at her son's graduation.
Junior?
Yeah, that's correct.
That's a bit more.
Okay, good, you're good. So,
Yeah, for the
before we get started, right, you guys can move up to the front if you wish to. So here's some ground rules through the day today, right? So all students have this, orange form. As I mentioned to you yesterday, I'm requesting each of you to fill out one of those. You have 3 per sheet, so fill out one for each student that you hear. And then the part that says score, ignore that score. It's only the rest of the thing that I want you to fill out for each of your fellow participants, right? And for the others who are evaluating, you should have a green form in the back. I want one form to be filled out per student, and it gives you a little way of computing a score, if at all possible. If you can compute a score and write it down, it will really help. And when you're done, you can drop it off in the box there that says completed forms. So we'll do one per student. And we're shooting for about 15 to 17 minutes of presentation per student. Now, before we get started, I want to just do one thing. We had a person in this team, this is the 3rd year of this REU, Dr. Flerchek. He was the one who was sick, and we had to, somebody else taught your class. Remember the Python class? So last weekend, Dr. Flerchek passed away. So I just want to take a minute to, moment of silence for him. Thank you. Dr. Flerchek was the computation science and engineering department, and he was very well known for supercomputing. Okay, with that, let's get started. And first, we have Nina here. The setup is we do not have you cannot see a presenter screen, so you have to look at this. Maybe advantage is to be in front of the podium. There's a clicker. There's a timer we'll set to, you can set to 17 minutes on another computer here, a laptop, and then you can watch that with that, let's get started. Thank you.
Good morning, my name is Amina Abdurrahim, rising senior IT major at Winston-Salem State University, and today I will be presenting my proposal on sentiment analysis on interdependent social networks. So my outline, first I'll be discussing the introduction, which will cover the background regarding the topic that we have chosen, the research problem statement, which will cover the problem being addressed, the obstacles that previous researchers have faced, the motivation behind conducting this research, and then the solution to the problem. Then I'll cover the research goals, the 3 key papers used, the methodology, approach, and tools, and then I'll end with references and a questions and answer session. So throughout history, there have been numerous accounts of criminal activity. And these activities can range from petty crimes such as theft and vandalism to much more serious ones such as drug trade and human trafficking. Some even have agendas that can incite violence and corruption that can weaken the structure of a nation. Now, in the past, all these crimes were capable of being committed, but today they have an advantage. The age of information and technology has allowed criminal organizations to expand to locations across the globe. This has allowed for communication, infiltration, the ability to hide both their location and their identity, as well as recruit multiple members. Now, where we once had remote organizations, we now have many clusters of criminal networks. And this right here, anyway, this picture is basically just showing the various networks of various criminal criminal organizations and where they are trading their products or services to across the world. So from the harm it can have on local communities and people to the harm it can have on the national defense and security, many government and law enforcement agencies are trying their best to work at dismantling and disrupting criminal network structures. Now, they are also using technology to their advantage, so they are using public police databases as well as bright networks. Now, bright networks are basically online communities. So what they want to do with these online communities is basically analyze the sentiments of the posts that they find on them. And this right here is basically an example of a criminal network, and it's Blackbird, which is a criminal network located in the Netherlands, where they were participating in the cultivation of wholesale marijuana. So the problem we want to address is how can we effectively use bright networks in order to disrupt and dismantle criminal networks. Now, the purpose of this is to be able to identify the criminals within the organization, understand what their position is in the organization, as well as their function, and then be able to use the data that we collect and find the connection between various users within that organization to lead to the dismantling of the organization as a whole. Now, despite the progress that has been made thus far using social network analysis, there are many inefficiencies. This includes it being time consuming. So while they may find useful intelligence, they may not be able to get it in time for them to actually use it with their case. Then there's the problem of the data being questionable as far as its reliability. So while they may have this data, they may not be able to connect it with the data they collect using other strategies. Then there's a difficulty detecting modules. So modules are basically communities. So think of like the people you go to church with, or if you're a fan of a specific person, like I'm a LeBron fan, I would belong to the LeBron community. And then there's the problem with the functionality. So because their communities often overlap, it's hard to tell what the function of that community is. So the motivation behind conducting this research is that there are consequences if actions are not taken. So consequences include that there will be an increase in the use of bright networks by organized crime, as well as greater difficulty in detecting this illegal activity. This is because the longer criminals use online networks, they will figure out how to hide even better over time. And so this picture here basically represents the World Wide Web. And so at the top, you have your regular web, which is where we tend to operate on a daily basis. So it has your email, your search engines, and your social media networks. Now below this is where things start to get a little dirty. So not the complete bottom of the iceberg is not that. It's called the deep web. The top layer of it is mostly just databases used by government agencies and larger businesses. But below that is where the illegal activities tend to happen. So that area is called the dark web or the dark net. So this is where you have activities such as drug trades, human trafficking, child pornography, and things like that. So just to give you an example of a real life scenario that happened in the dark net, there was a case in 2016 where a man named Richard Hurt was actually arrested because he was operating a child pornography website. This guy had over 45,000 people in his network swapping videos and images of child pornography with each other. So this is just to give you an idea of how serious the dark net can be and why we need to find a way to dismantle it, or at least some of the organizations that work within it. So the proposed solution is to be able to expand the capabilities of social network analysis, and we want to do this by using sentiment analysis combined with network optimization. So the research goal is basically to combine sentiment analysis with social network analysis, and we want to be able to implement it on Twitter posts. And then we want to be able to use that information to figure out how these users are connected based off of the sentiment of their posts as well as the content of it. The second thing we would like to do is be able to identify these modules or communities of interest and figure out who is at the center of them. And so this picture right here is basically just an example of a social network diagram. And at the very center, you'll see this little dot. And this just shows that this person has the highest centrality. So that means that they are the most important person within this network. And that's the type of person we want to be able to identify in the long run. So we want to be more specific. We want to learn and implement sentiment analysis on Twitter. Then we want to be able to determine the correlation between the users within that network on Twitter. Using that information, we want to be able to construct a graph that depicts the network and then identify the communities within that network that has users that share the same sentiment. And from there, we want to be able to categorize these activities as either normal, suspicious, or illegal. So there are 3 key papers that we used thus far in our research to kind of give us a background on what we want to do and what has been done thus far. So the first paper is titled Detecting the Overlapping and Hierarchical Community Structure in Complex Networks. Now this is basically gave a framework for an algorithm on how we can be able to detect the various overlapping communities within a network as well as the hierarchies between them. It covers the method, procedure, and variation of resolution parameters within this algorithm. And the usefulness of it is that it shows the computational side of network analysis. The second paper, which came out more recently in 2015, is titled Approaches, Tools, and Applications for Sentiment Analysis Implementation. Now this basically gave the main components that are necessary to successfully implement sentiment analysis. It gives us information regarding the process to analyze sentiment data, the various classification levels, as well as the features, techniques, advantages, and limitations that come with using sentiment analysis. Now this is a good article because it shows us how we can incorporate sentiment analysis in an advanced version of social network program. The third paper is probably one of the most important because it gives us a background on what has been done thus far. So this paper is titled Social Network Analysis Applied to Criminal Networks, Recent Development in Dutch Law Enforcement. Now it focuses on how the Dutch law enforcement agency has already been implementing social network analysis in order to apprehend such illegal types of organizations. And so it gives a case study on Blackbird, which is the organization I mentioned earlier in the presentation. And then the paper covers the advantages, limitations, and challenges that come with having social network analysis trained analysts. And so this paper is very useful because it also gives us the ability to learn how to interpret and apply the data that we will find using this program and be able to use network mapping. So this is basically a diagram of the methodology that we'll be using to conduct our research. So the first thing we want to be able to do, obviously, is learn and how sentiment analysis and social network analysis works. And then we want to be able to find the best sentiment analysis program that works within Python. So the thing is, we don't want to have to reinvent the wheel. There are multiple sentiment analysis packages that are already made. So basically, we'll find the one that works the best and use that as the basis of our overall program. We'll then combine that package with social network analysis and then conduct the analysis on the Twitter posts that we find and then determine the correlations between the users. Then we'll design an Eagle network map. Now, an Eagle network map is basically a social network, a map of a social network, and it has one user at the center. And based off of that user, we'll figure out how it is that they perceive the users around them and their actions. And using all this information, we'll draw conclusions using the data. So the approach that we want to use is, again, we're going to implement sentiment analysis on Twitter posts. So we want to focus on the posts that actually act the person. So that way we know that they're actually directing their comment to a person and not just in general to everybody. And so with sentiment analysis, you're going to see whether or not a post has either a positive tone, a negative tone, or a neutral tone. So if there's a positive tone, that means there's a positive correlation. So that means they're either friends or they're at least on the same side of a topic. If there's a negative tone, that means there's a negative correlation. So they're either on opposite sides or they're not friends at all and they hate each other. And yeah. So if they're neutral, that means there's no actual visible correlation. So they probably don't really know each other, they just happen to connect at that moment. So from there, we want to be able to examine these followers as well as the relationships they have with each other. So the specific user we're looking at, they all have their followers. But then we want to look at the one follower, and see how that follower connects with the other follower of that individual user. And then see the overall connection between them all. From there, we want to be able to model an Eagle network that would depict the connection that I'm talking about. And then we want to use the computational tools that I'm going to mention in the next slide in order to do graph theory and optimization problems. So all of these tools here are Python based. So obviously we're going to be using Python, which is a programming language, but we're mostly using it because it contains various packages that are going to be useful to our computational studies. Then we want to have centrality. So this is basically where the study of who is the most important, so who has a central role in a network. So you want to look at kind of like this area right here. So then we'll have normalized cuts. So this is basically where you're going to break down a network into its components. So the components are going to consist of the communities within that network. You want to look at the major communities. That's why this image kind of breaks it off from where you have like these scattered areas and then you have like a kind of set community, so it's like a patron community. Then you want to have Twitter, which is what we're going to use to get our posts from. And then there's interdiction, which is basically the study of the removal of a certain entity from a network and seeing what effect that removal has on the remaining diagram. And then we have Gurobi, and this is basically just an optimization problem solver program that we're using. And these are my references. Questions?
Did you talk about the data set you're going to use?
The data set.
Yes, for your research. What data set would you use to do the analysis?
Could you clarify that a bit more?
Meaning, what data are you going to apply your tools on, your analysis on?
The analysis?
Yes.
If I'm thinking of your question correctly, I'm guessing you're talking about like the information that we grab from the Twitter post. So like the content within that
Right,
post, so
right.
certain words that we're going to kind of pull out. So there's words like stop words, so you're going to have like your regular the, a, words that don't really have much of a
Not so much that
meaning.
detail, but would you take the general Twitter post that's available in public domain, or what is it? What are you going to use as the data?
That would be, I guess, the goal is just to take what we can have access to. Obviously, we can't just like hack into, private accounts and steal their information. But if it's open to the public, then we use that information to analyze it and then try to find the connections between it.
So let me ask this further. So once you know, like say, a Twitter feed from a particular, on a particular topic, let's say, how do you establish the networks that we're talking about to do any analysis? How do you know what the network looks like?
How would you know what it looks like?
Right, so you have these nice networks constructed, right?
Right.
So how would you construct the network before you do any analysis?
Well, I think the construction of a network would come after finding all of the users that we're going to be, I guess, analyzing. So you'll find the user and you find who they follow and whatnot, and then construct a network from there, and then analyze that network to figure out exactly how they connect. So when we look at the correlation between them, you'll see whether or not there is a positive one or a negative one, or there's no real one. They just happen to connect at that point. So.
Any other questions? We still have time. Yeah, you guys can ask questions too.
You mentioned a Bright network.
Yeah.
What is a Bright network?
Oh, that was the, I don't know, those online communities, so like your social media sites, your blogs and things like that. Anywhere where you can like post your opinions and whatnot and other information.
So you were saying some like major alert words that would be found on these websites, like how specific would these words have to be? Would they have to be like marijuana themselves, or like
It depends on the overall, I guess, specific topic you want to analyze. So if you're looking for drug dealers and whatnot, you'll probably add those into your list of keywords. If you were just trying to analyze like somebody's favorite sports team, then your words would involve like certain sports terminology or certain key players and things like that. So it just depends on the topic, and then you'll just create like a list of words that you want to use as like target words, I guess. That would kind of show their impact.
So do you foresee writing Python code, or you'd be using Python code that's written already?
Well, I know some of it will be written already, but in order to combine it, we probably would have to write a little bit of our own in order to make it work.
Any other questions? Very good, thank you. Yeah, you have a couple minutes left.
I got it.
Okay, so why don't we use this card, so you can Oh, anyone can pull out one of these walls in the back.
Oh, thanks.
That one, can you?
Who turned it on?
You both have one. Just take a moment to pull this out. Jared?
Dr. Ram, I sent you a modified version this morning around 9:30. Did you not get that?
Okay, I was looking to, did you send it to,
I sent it to you and I CC'd Felicia.
that didn't make it to this. Can you pull it up on that?
Yes.
That would be easier, I think.
This is the one you sent. I think it's put the same thing. Yeah. See. Can you see this? This is what you sent. Oh, I'm sorry. Yeah, I'm sorry. Okay.
There we go. That's the one. Yeah.
Yeah, it's huge.
So how do you think we should say this?
One second.
Switching devices.
Yes.
There we go. Okay. Sorry about that, everyone. My name is Jared Boggs. My mentor is Dr. Sunyi over there, with additional help from Dr. Theo Hansen, and my grad student is Mr. Peng Yu. My proposal, as you can see, is on improved leader-follower motions and adaptive cruise control for ground robots. I'll explain, obviously, what that means. Just a quick outline, just like the rest of you all. Go through an introduction, research problem statement, research goals, go over a couple of key papers, and then basically go about how I intend to go about this research. So we'll start with an introduction. I don't know about you all, but when I'm driving, especially going back to Greenville, it's about a 3-hour drive. I make pretty frequent use of cruise control. which you're all probably pretty familiar with. You just set the speed you want your car to go, and it stays at that speed. But a problem quickly arises, particularly when I'm in the left lane. If I'm getting close to the car in front of me, my car does not recognize that and slow down when I'm on normal cruise control. So how do we go about fixing this problem? Well, ACC, also known as Adaptive Cruise Control, adjusts the speed that your car is going at based on the car in front. So when it senses a car in front of you and say it's going 10 miles per hour slower, it'll slow you down so that you don't rear end the car in front of you. Obviously a good thing. Now, several versions of ACC already exist today. Multiple manufacturers have their own specially named versions, but they all basically do the same thing. BMW, Mercedes-Benz, Audi, Ford, lots of different manufacturers have their own version of ACC. Now, a similar, pretty well tied together concept is that of leader-follower relationships, and that's pretty closely tied with ACC. Basically, a leader-follower relationship, as you can probably guess by the name, means that one car becomes the leader and the other one becomes the follower. They essentially become one unit. They will switch lanes as one unit. They will have the same speed. They will speed up, slow down, whatever the case may be. They essentially become one unit, mirroring each other. So why am I talking about these two things? Well, aside from convenience for human drivers, I'm sure you've all probably heard of driverless cars or self-driving cars being the future of the automobile industry. And this is something that robotic cars will need. They will need to be able to recognize when the car in front of them is slowing down or speeding up. They'll need to be able to switch lanes to navigate. And so these two technologies are huge for the future of autonomous vehicles. They need to have these capabilities, and they need to be very well tested. So, my research problem statement. This video that I'm going to show you is taken by Mr. Peng Yu, and these two robots you see here are Turtlebot burger robots, and I'll get into them later on. But as you can see, car-like robots usually follow each other pretty well. That capability is pretty well tested out. But the movement of a follower is not always necessarily smooth. I'll show in the video that sometimes it's choppy. They speed up, slow down, or even just move, stop, and that's not something that you want a real vehicle on the highway to do. You want it to be moving continually. So this video is about 1 minute and 15 seconds. I do want to show the whole thing, but I'll explain why we need to watch the whole thing. So just for a second. Okay, now, so what can we see from this video, which is just a demo of the Turtlebot's follower demo that comes when you download the software necessary to run and control these Turtlebots. So you noticed at the very beginning, it did a fairly decent job of following it. When the leader moved, the follower moved. Now, if it was an actual car, you wouldn't want it to do that because you probably noticed it rear-ended the leader several times. But you will notice that as the leader, towards the end of the video, begins to speed up and keep a higher constant speed, that the follower had a harder time keeping up. The distance between the end of the leader and the front of the follower increased. That following distance, it generally increased. You'll also notice that the follower rarely got to a point where it was moving consistently, where it would set a velocity and stay at that velocity. Instead, it would start and stop and start and stop. And that's part of the reason why, over time, the following distance gradually increased. So the question basically becomes, what's the best way to make this movement more smooth? This research that I'm going to be doing is going to try to find one such way, one such function that we can develop in order to make this movement more smooth, something that an actual car would want to follow. Obviously, no rear ending is going to be involved. So the function that I intend to make is based on a distance-dependent function, specifically the following distance. And as you can see by these beautifully drawn graphs that I made, there are several different ways that you could make an ACC function. You could have one where you want your robot to be, or the car, you want it to be at the same position that the leader was, but a second or 2 seconds later. You could have one where it reaches the same velocity a second or 2 seconds later, or you could have one that reaches the same acceleration. So there are a number of different factors that you can use to base your function on in order to create this ACC function. The question is, which of these is the best, which is going to have the best performance? So as I said, the research goal, improve the follower movement from stop-start to fluid, create a distance-dependent ACC function, and then obviously within that ACC function, we want to plan for the kinds of things that come up when people are driving. Accidents happen. You do need to stop suddenly. You may need to get into another lane suddenly. These kinds of things happen, and so you'll want to be able to plan for that. So a couple of key papers, both out of universities in Germany. This first one from the Technical University of Munich. They used a number of factors to create an ACC system or an ACC function, including following distance, the comfort level and safety of the passenger and other motorists, and also the jerk involved in sudden movements and sudden changes in movement of the car. And as you can see, they focused on safety, which is pretty applicable to an actual automobile company. Obviously, they're going to want to keep their customers, their passengers, their safety is the number one priority. So as far as application in my research, I'm going to create a similar system or a similar function and model for an ACC based on following distance. As you all saw in the video, the robots don't really get up to breakneck speed, so you don't have to worry about stopping distance or anything like that. And obviously, you won't have to worry about passengers because they're robots the size of a water bottle. But it is the main point is that a similar system is going to be created based on following distance. Now, another paper, this one is from the University of Kaiserslautern. They had a similar process. They also came up with an ACC system based on a number of factors, including uncertainty and all these different factors, but their main focus was trying to maximize or find the optimum balance between energy consumption and the computational power required. So what that means is that in one scenario, they would map out a route before they started, and the only computational power that they would use is to react to traffic as they're going. Now, when they did this, obviously, less computational power is required, but they did use more energy because they couldn't find that optimum path as they went along. Now, they ran another trial where the opposite was true. They continually, as they were going along, tried to find the best path. Now, this resulted in a drastic decrease in the amount of energy that they used because they could find that optimum path as they were going. So in terms of application to my research, the function that I create will also involve a balance of how much energy the robot will use to move around and also how much computational power is required, especially in the Turtlebot's G mapping feature, where it uses the LiDAR, which is light detection and ranging. Basically, as it moves around, it can detect the environment around it, and it can create a digital map of that. Once that map is saved and then reloaded, it can then, once the user specifies a point in that area, it can navigate to that area. If you have a leader-follower or an ACC relationship, then if you have two robots, they can navigate to that point. Since the leader is the only one that has to figure out and compute what path it has to take, the follower uses much less computational power and much less energy. So you're really optimizing the movement of the follower. And then finally, talking about my general approach, how I'm going to go about doing this, the tools I'm going to use, that sort of thing. I'm going to be using Robotics' Turtlebot 3 burger model. As you can see, this little guy right here, 2 wheels, the LiDAR sensor on the top. It's got a ball and socket at the back to keep him upright and help him swivel around. It's a great little robot, very modular, very cost effective, very good for research. It's great for education, and a very good just general purpose robot. Very simple, very easy to modify and create code for. The follower demo that I showed you a video of, that's going to be my starting point. I want to go in there, see the way that it takes the information that it receives from the LiDAR and how it reacts to that. Once I have that information, I then will edit it using the ROS, the Robot Operating System, which is just like any other programmer. Just type in the code. You can edit the code in any sort of text processor, just like the Notepad on your computer. So once I'm able to modify this code, and once I understand how it works, how the information from the LiDAR is then processed and then given velocity commands to the robot, then I'm going to go in and use differential functions and just first or second order, just simple functions in order to model the position, velocity, and acceleration of the Turtlebot. That will allow me to understand, okay, here's the following distance. If I want to get to a certain following distance, what does the velocity need to be? Does it need to be higher? Where does that point need to be? This will most likely be some variation of MPC, which is model predictive control, or PID, which is proportional, integral, and derivative controller. So basically, the PID controller takes a point that is desired and then finds the error between that desired point and where it currently is, and then it tries to give commands such that the difference is reconciled. And then the end goal, have another video clip like the one I showed you, but ideally this one will be the two of them moving as one, pretty much in sync, and definitely not choppy and inconsistent like this original demo. Also have a distance-dependent ACC function, which I imagine will be a series of if loops. So for example, if the following distance is within this range, set the velocity to this certain meters per second or whatever the case may be, and then have different portions of the loop such that it can account for whatever the distance may be or any obstacles that may come up. So here are a couple of my references. Everything is cited in IEEE, I believe. And that'll be it. Thank you very much. Questions from anyone?
So Jared, let's say you get your turtle robots working.
Yes, sir.
Now, the performance, doesn't it depend on the payload? Meaning, if I put some heavy load on the turtle robot. In other words, the algorithms have to also consider the mechanics and dynamics, right?
Mm-hmm. Yeah, that would that's something that I will probably consider later. I want to get to a point where, as they are, just the leader and the follower, no additional payload, because they're not really designed to carry anything, but obviously scaling them up want to get to a point where they're moving more consistently, and then we'll get to a point where, or I will get to a point where I can say, if it's not moving the way it should because of the payload, then you can increase the velocity to compensate.
So you mentioned in the beginning that there are two technologies, ACC and the leader-follower.
Yes, sir.
Is there a difference, or is one subset of the other?
I would say the leader-follower relationship is probably a more broad way to describe ACC, or ACC is within the purview of leader-follower relationships, but there's so much more that is involved within leader-follower relationships, much more concerned about if it moves in a different axis other than forward and back, that within the leader-follower relationships, the follower will be able to move, whereas ACC is really just concerned about distance in one axis, or the velocity. Sorry.
That was excellent. That was very interesting. Thank you. I have a question on the basics of ACC. So you said earlier that you can treat those two units as one. I think that you were exaggerating a little bit, right? Okay, perfect. Yep, I get that. But you said that like when one changes a lane, the other one changes a lane. When do you recognize that, let's say you are the leader and you find the car in front of you, how do you recognize whether you have to change the lane or they become the leader and you are the follower, and then you end up with a 3, 4, 10 unit?
Yeah, that'll more determine on, or that'll be more based on communication between the cars or the units within that relationship. This research is mainly focused on if you have the follower, you'll sense the one in front of you. So in a sense, each one within can be a leader. And
leader, follower, leader. Yeah. Okay. So basically that would also have to do with navigation, I guess, where you're going to, right? So that's the communication part. I have a second question as well that I didn't really get that much. You said that the leader calculates a lot of the information, so the follower like saves on computing time, right? In dynamic program, first of all, you mentioned dynamic programming in one of the technical papers. So dynamic programming is very expensive, time consuming.
Yeah.
Are you going to be able to do something like that in a Turtlebot, or is that an idea for the future?
That would probably be an example of scaling it up. But actually within those papers, they actually tried to blend, because like you said, dynamic programming is so computationally demanding. They tried to combine it with both PID controllers and MPCs to try and get that computational power down.
Thank you.
Very good,
Very much. Really? Yeah, I was like, shoot, I'm talking really fast.
Hello, my name is Walker Cherry, and this is my presentation on the classification of acoustic emission signals. So a brief outline of my presentation, we start with an introduction, like what is acoustic emissions, we go into what the acoustic emissions effect on non-destructive testing is, and we'll go into its history, and we'll go into my problem statement, how do we classify acoustic emission signals, and onto my approach to this problem, and in conclusion, I'll go over the key papers and references used.
Could you speak up a little bit?
Oh, my bad, sorry.
Yeah.
So, what are acoustic emissions specifically? Well, acoustic emissions are the elastic waves released when a machine or structure undergoes a certain level of stress or releases energy. Like us, machines talk when they're in trouble, and more specifically, this is like larger when there's a more permanent or irreversible damage to the machine. Whenever an object performs any action, there is a sound being made, and an acoustic emissions tester generally just finds this sound and try to attribute it to what kind of damage is being caused. At a basic level, we use acoustic emissions all the time. With events such as squeaking doors, we want to oil the door now because we want to get rid of the squeak, breaking glass, or even the sounds coming from our own bodies. Popping joints or even our digestive noises are examples of acoustic emissions in our daily lives. So, into non-destructive testing, using acoustic signals to determine the integrity of a machine has become the preferred method due to its non-destructive nature. Non-destructive testing is when you test the machine, its inner workings, without damaging the machine itself. For non-destructive testing, destructive tests were used, and they involve using samples instead of the actual machine in use. This would be proven to be not as accurate as machine, because since we would not be performing and not doing the actual action that the machines would be doing. Another drawback to using destructive tests is that if you actually test the machines themselves, should you find no problems with that machine, you'd be either interrupting its progress or, worse yet, destroying the machine for actually no reason at all, which would be a potential loss of revenue or even worse. So, a bit of a history with acoustic emissions. The first uses date well beyond the even start of technology, with the first uses being in 6500 BC with the use of arts and crafts. Crafts such as pottery were used to frequently test their products using, by tapping their crafts, they would usually listen for cracking noises or other things that would indicate a non-uniform drying of the clay that the region was used. Technology-enhanced uses of acoustic emissions began in the early 20th century with reports of specific audible sounds being linked to material damage. For example, in 1923, a researcher named Le Chatelier was able to report that he was able to detect a high-frequency sound that was emitted when he deformed a plastic and aluminum alloy. During this time, most experiments involved using plastic or wood, and since these materials were usually easier to detect, and the technology simply just wasn't there to detect hard metals and solids. More modern uses of acoustic emissions include when Dr. Steele used it to determine the integrity of rocket motor capsules in 1961 for the US Navy. Later, Dunnigan also began to use the acoustic emissions technique for submarines and high-pressure vessels in 1963. And his development continued until he was able to form the first acoustic emissions company, Dunnigan Enterprises, in the United States. Acoustic emissions during this time mostly involved military use, since the fact that destructive tests were actually simply just not an option. You couldn't interrupt the military vehicles in operations at the time, and you certainly couldn't dismantle them. So today, the technique is more widely used, and not only for military use, but just in general use today. And there was actually standards developed for testing certain materials. These standards would include achieving a 100% examination of a structure without interrupting its process, or even just simply testing frequently repaired objects instead of objects that were sparsely repaired at all. So the big problem with acoustic emissions is that now that we determined that it involves listening to the sounds that machines are making, machines make noise all the time. We need to determine a way to find out which noises mean which things. The problem becomes we need a way to differentiate between the signals we detect. Machines making constant noise makes it harder to detect signals that represent failure, and because of this, we need to find a way to classify these specific signals. The goal of my research is to determine a way to simply just categorize these emission signals in terms of things such as what they are, where they came from, and the level of threat that they pose to the machine themselves. Waves propagate at different speeds, and this can be used to differentiate between the certain materials that we have. They refract at different directions, so we can put signals in different areas to define which signal means this type of damage here. Waves that are benign would generally be ignored, while waves that are harmful should have their source location looked at more intently. The method I chose to go about doing this, solving this problem is the cluster analysis method. The cluster analysis method generally involves naturally grouping all detectable waves that we get from the source material and grouping them in terms of their similar properties or similar characteristics. These would include things like wavelength, frequency, or simply just where they came from. This would make the task more recognizable to speech recognition in the sense that we're simply just trying to match the waves with the harmful ones or with each other. To solve this problem, we need to identify a correlation between the waves detected. The code I created was using MATLAB and later on in C++ that would basically just use data points acquired from the waves that we take in and create a matrix of the data points to find a pattern among these waves and find a correlation. Specifically, it just takes in the data points from the waves and puts them into a matrix to find a pattern. The pattern would later be used to find like a correlation between later waves that we would detect, and they would group them together, similar to finding a regression model in statistics. Right. The output from the code is generally just a long list of clustered waves similar to this right here. As we can see that these three waves together have similar characteristics. And more importantly, these 4 or 5 waves right here have large characteristics among each other. And since they are significantly larger than other waves, other clusters, we can assume that these waves might indicate harmful waves, since louder signals and more common signals indicate a more harmful detection of waves. The next part of the code simply just takes apart all the clusters that we get and just prints them onto the screen. This is an example of a cluster that we got right here from the data points that we got. And as you can see, these action sites right here, 225, 248, 250, and 342, and 404, these sites right here indicate that there may be a problem at these sites and that we need to go and check out what's happening at these wave spots. To conclude, acoustic emissions are the sounds propagated from a structure that undergoes a significant level of stress. Acoustic emissions is a form of non-destructive testing that involves testing performing materials instead of sample materials, and without dismantling them or interrupting their functions. Using acoustic emissions also demands the need to organize the sound waves that are detected by using the cluster analysis method. I can group waves with similar properties together, with the largest group more likely to be more harmful to the actual structure itself. The key papers I used were these papers right here with Dr. Moragan, simply showing me that with the history of acoustic emissions and showing that basically he chose a different method of going about doing this, and it was a little bit more complicated than I felt that I was capable of. So he chose to actually just straight up match the waves that we got with signals that were already detected to cause harm in the machine. This would be a little bit more specific in the way, instead of just simply clustering the waves and finding out then, he would straight up just match the waves immediately with harmful waves. This would mean that you would have to test each wave individually instead of groups of waves, which was a little bit further beyond what I was able to do. Down here, we can see that the clustering of emission signals was introduced in 2004 by Dr. Godin. And that was the method I chose to go about solving this problem. simply because it was just a faster method and it was more efficient in the sense that I could actually find these waves and match them in smaller groups, and it was more manageable in the time period that I was allowed. Any questions if you have any?
What machine are you going to be testing?
We would test multiple materials. The starting material was aluminum fiber, and then the actual process would be to just simply snap the fiber at specific points, and then record the sounds from that point right there.
Do you have a database of these files, or are you gonna have to go in?
I have a database on my flash drive. I chose not to include it because I actually tested 30,000 points since I've gotten here, and that would take literally forever to go through all of them. But I do have a database that's on the flash drive. Yes.
When you say cluster analysis, right, what are the factors that you're trying to look at in cluster?
We are actually measuring a correlation between the waves. We would just simply look at the pattern of the waves have and look for waves with similar patterns or similar attributes, just like the wavelength of the wave or how the frequency of the wave itself. That was just, those are the factors that were used to cluster the waves themselves.
Frequency and wavelength will end up being just one factor, right?
Yes.
So what other factor do you have besides that?
It would simply just the pattern that the waves have, also the location that they came from would also be used. Since we can have the one sensor right here, and then there could be multiple cracks on either side, and we could use, this sensor could detect waves from different sides right here, and we would need to understand that their location is also another thing that could cluster these two things together, because these two waves could also have similar properties such as wavelength and frequency, like you said before. So we would want to understand that these waves came from this location right here and should be grouped together versus these waves right here.
So how do you find the location? Meaning, this is data from experimental setup, right?
Mm-hmm.
So how do you know the origin of that wave?
The cracks are actually done one at a time. So when we do the shears, the waves that came in earlier are from this location right here, and we only detect up to about 500 or 1,000 from this specific spot. So we would segment them in groups of 5. I did 500, but I'd segment them in 500, and then so all the waves from 1 to 500 would be from this location, and waves from 500 to 1,000 would be from this location right here. And that's how I group them by location.
Let me ask you one last question.
Sorry, it's fine.
So the clustering algorithm and code, do they exist? Are you going to create them
yes.
and code them, or what?
The code was given to me in MATLAB, and I just worked on improving it to find the cluster specifically for what I was doing. And I was working on redoing the code in C++ and working on doing that right there. And so basically what I did is I improved the code to find the specific clusters for 500 data samples in this location and then 500 in this location, instead of just finding all 30,000 at once, like beforehand.
I apologize for doubling down on the clustering, but I think that this is a key part of your work as well, so I have a follow-up question on this. You said that you look at the pattern. Do you treat the waves as if they are like time series, basically?
Yes, we would find that the data points acquired are just basically they're a specific point after over an interval right here. So a wave that would have a certain pattern right here would also be measured later on with a similar pattern over the time period that we would detect. Yes.
Delay the sensor.
Yeah, delay the sensor.
All right, thank you.
Yeah, sorry.
No, you're fine. I'm just thinking out loud.
Yeah.
Thank you. So we'll break now for the lunch. For your, if you have lunch and come back here, we'll start again at 1. Okay? Get there a couple minutes before. Get here a couple minutes before.
I'm holding on to those.
I'm gonna hang on to mine.
How's the geology?
Yeah, you got it. Eric, you go back to the door.
Yeah.
All right, I'll drive back.
You see it? You go zoom in at all? No, it's. It's all good.
I'll follow you up. Call your bluff.
Thanks a lot for coming. And meeting the actor.
Yeah.
You